All right. Okay, so class had a lot of technical difficulties today. And I think I have screen sharing figured out, sort of. I think Monday will be an adventure too when it comes to sharing on Zoom, unless Zoom magically fixes itself. But anyways, without further ado, we'll just get to our midterm review. So our midterm is going to start at the end of chapter 3. So the parts of chapter 3 that we didn't test with midterm 1, and carry us through to the end of polynomials. Okay, so our first example is to graph this function. F of x equals 3, x minus 1 cubed plus 1. The first step in these problems is always to identify the parent function. The parent function is the basic function that we know how to graph. So here, this function kind of looks like a cubic. It has an x cubed term. So our parent function is g of x equals x cubed. Now we can draw the graph of g of x equals x cubed and then apply transformations to graph f of x. So g of x equals x cubed has points at 1, 1 and -1, -1. Our first transformation is going to be dealing with this -1. For all of these problems, I'm going to go right ahead and just say what it is. But you should take a second, pause the video, and think in your head about what the transformation is going to do. That will be a very effective way of studying, as opposed to letting me just guide you through the whole thing. And so the x minus 1 means that we have a leftward shift. And hopefully you all caught that that is incorrect. We actually have a rightward shift by 1 unit. So now we have the point 2, 1 on our graph and 1, 0. Okay, our next item is tackling this 3. That's a stretch, a vertical stretch. So now instead of having 2, 1, we're going to have 2, 3. Instead of having 0, -1, we'll have 0, -3. But our root still stays at the same place. So we just get stretched out. And that's our graph. And then finally, we need to take care of this +1. That's just a vertical shift up by 1 unit. So it's going to look just like the yellow graph, except shifted up a single unit. And so this red curve is our final graph. All right, capiche. Now let's move on to our next example. This is a very different looking function, but it's important to think about similarities of how this problem relates to the previous one. We're still going to start off with finding a parent function. In this case, our parent function is the absolute value of x. And we'll sketch that. Just like that. And now our first transformation is this -2. The -2 actually does two things at once. Think about what those two things are. Okay, so we'll label a couple points on here to make our transformations clear. So first we have points at -1, 1, and 1, 1. And now when we apply that -2, we're going to pick up points at -2, -1, and at -2, 1. So not only do we reflect, we also become sharper. And then finally, we need to deal with this -2. That's going to be a vertical shift downwards by 2 units. And so we end with this red curve. All right, and that's graphing. So we can expect a problem that looks similar like this on the midterm. So something where you identify the parent function, and then you identify what each transformation does, and use that information to find the graph. Okay, so then chapter 4 was actually a bit of a detour. We started with data, because you have to stick this somewhere, because data is a really crucial thing to learn about nowadays. So why not just stick it in chapter 4? So we started off talking about correlation, and now there's a few main topics in correlation. So we have correlated data and uncorrelated data. And within correlated data, we have positively correlated and negatively correlated. All right, so think about what you know about correlation and determine what's the correlation of this scatter plot I just drew. This one's actually no correlation. So it's correlated when you can predict one value given another. But this one, if we knew that the value of x was 1, we don't really have any insight into what the y value is. It could range from down here at -5 to up here at 10. And that knowledge doesn't really change if we made x bigger or smaller. Meanwhile, there's correlated data. So let's draw an example of a correlated data set. So this is data that's pretty highly correlated. And this is positive correlation. And when we have correlated data, we can find the line of best fit. And that helps us predict what our values are going to be. And here's what that means. In this case, if x was equal to 1, we're up here at this point, that could be 10. And we expect x to, our y is about 10. Maybe it's between 9 and 11. But so it's pretty close. And if we change x, our y value changes significantly. So if instead we set x equal to -1, and we looked at our y value, now we're getting y values such as -4 is less than y, it's less than -2. So you can use x values to predict y values. And it's positively correlated because as we increase x, y increases as well. Or likewise, the line of best fit has a positive slope. our final example is negative correlation. And so here, the only difference is that our line of best fit has a negative slope. So as we increase x, that tells us that we decrease y. That's negative correlation. Now here we're actually a little more weakly correlated, but still correlated nonetheless, because we can make this line of best fit. But because the data is a little bit more spread out, it's harder to predict what y is based off of knowing what x is. Unlike above on our positive correlation, where our y's are much closer together. And now what counts as close together or not is totally just subjective to the scale you're working on. If you're estimating the size of atoms, then if you're off by even like 1/10 of an inch, that's crazy wrong. But if you're measuring the distance between stars, then being off by an inch isn't such a big deal. Okay, and one thing that happens with data is we actually don't always want to use a line of best fit. So one of these ideas is that sometimes we want to find a quadratic that fits best. So usually what will happen is if you're working with simple enough data, you can just plot the data and that will be enough to see what kind of curve you would want to use. In real life, especially with working with high dimensional data, it can be nearly impossible to figure out what kind of curve fits best. And that's just one of the challenges that data scientists face today. So that first one is clearly quadratic. The second one, again, a line is going to be best. This third one, we have two options here. And this is something else that data analysts argue about, is whether you'd want to use a line for this data, or if you want to use some sort of a cubic. And so here for this data, cubic is probably better. This field of study is known as talking about overfitting. You don't necessarily want a curve that fits your data too well. And let's give like a reason for this too. So if you didn't have that much data, so let's say your data points look something like this. You don't have that much data, but it kind of looks like you should use a line that looks like this. That would be a pretty good fit for your data. Alternatively, you could just use a really high dimensional polynomial, one that fits the data perfectly. And have that be your model. That'll predict all your observed data points excellently, except it's probably going to be really off for any x values outside of this range. Like if we picked an x over here and we walked all the way up our curve, it's going to say our x value should be huge, even though if we were using that line we had before, something that looks like this, it might actually say x is negative. Anyway, so that's just kind of an interesting topic that people think about is how big of a polynomial do you actually want to use? This case, when we have a lot of data, so that back to this cubic case, when we have a lot of data and it still exhibits this cubic pattern, we probably want to use a cubic. And finally, our last ones, we'll want to use a line for that. All right, so let's just label this as overfitting and continue on. We had some optimization problems that we talked about. We had one really, really gnarly one about the Norman window. Yeah, that's not going to be on the exam. I'll just say that right now. I'd expect all of you to be able to do that as a homework question, or I could give it to you as a take-home question, or it could be the only question on the exam, and you could do it. But for giving a regular exam like I'm doing, it's not really reasonable to expect you to be able to figure that out. Just because you only have about 10 minutes to do it, and that Norman window, if you get, it's so easy to get a sign error there that it's better to just test on simpler problems. So here's one. We have a pen, we want to build a pen for our horses. We have 1,000 feet of fencing. The question that we want to answer is if we have side lengths x and y, what dimensions should we choose for x and y to maximize area? That way our horses have as much room to play. So what we actually get here is a quadratic. We have that our area is x times y, and our perimeter is our constraint. We know that 2x plus 2y has to equal 1,000. That's because we have a rectangle. So that's just perimeter of a rectangle. So what we do is we solve for y and plug it into area. That way we only have a single x variable. And so we can find that y equals 500 minus x. So then our area is x times 500 minus x, which is 500x minus x squared. Now what we want to do is optimize this. So we want to figure out when this is maximized, because this is our area, and it's maximized at our vertex. So let's find the vertex. We can rewrite this as negative x squared plus 500x, and we'll factor out a -1. So we get x squared minus 500x. Let me put a little space so we're not distracted by what's on the bottom. And now what we have to do is add something and subtract something, so that way we get a square polynomial. Remember, we always take our 500, we take our b term, that's our -500, we cut it in half and we square it. And that's what we add on. And we also have to subtract it so we don't change our equation. And now we can reduce what this is to just x minus 250 squared plus 250 squared. So our vertex is 250, 250 squared. So it says that for our pen, we'll actually want it to be a square because our x side length should be 250. Our y is 500 minus x, so that's also 250. Then our area is 250 squared. So that's what maximizes it. So that's pretty awesome. All right, let's look at another problem. Here we're selling broccoli at a farmer's market. We estimate that we can sell 300 minus 100x heads of broccoli when we charge price x. So this Q is standing in for quantity. Our question is, what should we price our broccoli at to maximize revenue? Well, the very first step is to write down our revenue function. Our revenue function is x times Q of x. So that's price times quantity. That makes sense. The amount of money you bring in is however much you make per item times the number of items you sell. So if you sold 10 heads of broccoli at $3 a head, you would bring in $30. So here our revenue function is R of x equals 300x minus 100x squared. And in this case, we're not going to do all the completing the square. We're going to use our vertex trick. That says that our vertex is minus b over 2a. Actually, I think it's just b over 2a. Minus b over 2a. F of minus b over 2a. So here our b is 300. Our a is negative 100. You can figure out this negative because we wouldn't want to price our broccoli at a negative amount. So we get 300, negative 300 over negative 200, which is negative 1.5. So it says we should sell our broccoli at $1.50 a head. And then our revenue is f of negative 1.5, which is 300 times negative 1.5 minus 100 times 1.5 squared. Negative 1.5 squared. It's going to be negative. Oh, I'm sorry. This isn't negative. That's positive 1.5. That'll make everything work a lot better. So our revenue here is 450 minus 100. And if you're good with your squares, you know that 1.5 squared is 2.25. And so this all comes out to just 225. So we sell broccoli at $1.50 a head, and we earn 225 bucks. It's not bad for a farmer's market, I guess, depending on how much they charge you for a booth. All right, and then on chapter 5, we had polynomials. Our first question is figuring out what the degree is, and then we'll move into examples of graphing. So here, when we have a polynomial in standard form, our degree is just the biggest power. So our degree is 5. Our second one is this mixed form. So we're going to have to be a little careful about what the degree is. But try and think about if you can reason out what the degree is in your head. Okay, so the degree here is 4. And the reason it's 4 starts out with 1, we have this x cubed here. We're not going to worry too much about that, because when we expand this x minus 2 to the 4th, we're going to end up with a 4th degree term in there, and not a 5th degree, because we'll never multiply like 5 x's together. So our degree is 4. Finally, we have a factored form. And here we sum up the degrees of the top, the multiplicities. And so we get a degree of 5. So that's pretty good. All right, so now let's actually put our degree know-how to work. And we're going to graph this function. Okay, so the first thing we need to do is figure out what our roots are. And they come from each of these terms. So our roots are 2, -2, and 5. And so we'll just plot those roots on here. -2, 2, and 5. And we'll start graphing in yellow. We need to figure out our y-intercept. But that's just f of 0, which is -2 cubed, 2 squared, and -5. So that's -32 times -5, which is, that's a large number. That's 160. So we're up here at 160. We know that our graph has to do something like this. And now we can figure out what it does at each root by looking at the multiplicity. So at -2, we have an even multiplicity. So we're going to bounce. But at 2 and at 5, we have odd multiplicities. So we cross through. So our graph looks something like this. And this kind of makes sense because our degree is 6. So we know that end behavior has to look something like this, where it goes up on both sides. This also is because the leading coefficient is 1. So our end behavior looks like 1 times x to the 6th. All right, and now we were able to graph that before because we had a fully factored polynomial. We don't always have a fully factored polynomial. Sometimes we have to factor the polynomial ourselves, which we can do. So here we want to find all roots of this polynomial. And so to do this, we can start with the rational root theorem. That gives us a list of potential roots. Our leading coefficient is 1, and our denominator is our ending term is -3. So our roots could be plus or minus 1 or plus or minus 3. There's nothing to divide by them because our leading coefficient is 1. If that was a little confusing to you, go back and also review the rational roots theorem. So now we have 4 candidates for roots. And let's test them out and see what happens. So we'll just start with f of 1. And we get 1 cubed minus 5 times 1 squared plus 7 times 1 minus 3. And this is 1 minus 5 plus 7 minus 3, which is thankfully 0. So it's a root, which means we can factor out x minus 1. And so we'll start with some polynomial division. So first, what we have to do is match this x cubed term with this x. So we'll stick an x squared on the top. And then multiply that x squared to both. So we get x cubed minus x squared. And so we get a minus 4x squared plus 7x minus 3. Then we match the x to the minus 4x squared. So we get a minus 4x squared plus 4x. Subtract this whole thing. We get left with a 3x minus 3. And then finally we get a plus 3 to match the 3x minus 3 and a remainder of 0. All right, looks like we need to put a little space in here. So what we have is that x cubed minus 5x squared plus 7x minus 3 is the same as x minus 1 times x squared minus 4x plus 3. And now we have one root at 1, and we can factor this quadratic to get the other two roots. And now, so go out on your own and factor this quadratic, but it shouldn't be too tough to see that it's x minus 3, x minus 1. And so our roots are just 1 and 3. All right. And now that we also have a polynomial written as x minus 1 squared, x minus 3, we could also go through and graph it if we wanted to, but we're not going to. Okay, for our final problem of the review session, we're going to find all the roots of this 4th degree polynomial. And thankfully, someone has looked down from the skies and gifted you with 1 minus 2i as a root. But little as they know, they implicitly gave you another root, because you know that another root of this is 1 plus 2i. And if you don't know how you know that, go figure out how you know that. It has something to do with the conjugate root theorem. Okay, we hate doing polynomial division with complex numbers because we hate adding and subtracting complex numbers because it's tedious. And where there's more numbers running around, there's more room to make sign errors. So what we can do is multiply these two terms together and come out with a quadratic that will factor out. So when we multiply this together, we get x squared minus x minus 2ix minus x plus 2ix plus 5. And go through and check the work to make sure that that 5 is correct. But I'm fairly confident that it is. And we get an x squared minus 2x plus 5. And now we can do our polynomial division, but this time with a quadratic. Okay, so we first need to match x squared to x to the fourth. So we'll pick up an x squared on the top, and x to the fourth minus 2x cubed plus 5x squared. Subtract all of this, and we'll get a minus 5x cubed plus 16x squared minus 37x plus 30. And now we're going to match the x squared to the 5x cubed. So we'll need a minus 5x on the top. And what we get left with is a 6x squared minus 12x plus 30. Look, we write a plus 6 right there. And we get a 6x squared minus 12x plus 30. Subtract, we get remainder 0. So we factor as x squared minus 2x plus 5, x squared minus 5x plus 6. We already know from above that this first one is going to factor as having two complex numbers. And the second one, it isn't too bad to see that it's going to factor as x minus 2, x minus 3. So our roots are 1 plus or minus 2i, 2, and 3. So there we go. That's all we need to know about our polynomials. All right. Excellent. So I hope this review was useful. And I'll see everyone in class on Monday. And good luck on the exam.